Dear students, ਪਹਿਲੀਆਂ ਕਲਾਸਾਂ ਵਿੱਚ ਅਸੀਂ ਹਾਈਡਰੋਜਨ ਐਟਮ ਦਾ ਬੋਹਰ ਮਾਡਲ ਅਤੇ ਹੋਰ ਕਈ ਐਟੋਮਿਕ ਮਾਡਲਸ ਬਾਰੇ ਪੜ੍ਹ ਚੁੱਕੇ ਹਾਂ। ਇਹਨਾਂ ਦੇ ਇਲਾਵਾ ਅਸੀਂ ਹਾਈਡਰੋਜਨ ਐਟਮ ਦੇ ਸਪੈਕਟਰਮ ਬਾਰੇ ਵੀ ਪੜ੍ਹ ਚੁੱਕੇ ਹਾਂ। ਅੱਜ ਅਸੀਂ ਐਟਮਸ ਨਾਲ ਰਿਲੇਟਡ ਕੁਝ ਫਾਰਮੂਲਿਆਂ ਨੂੰ ਮੁੜ ਕੇ ਯਾਦ ਕਰਾਂਗੇ ਅਤੇ ਉਹਨਾਂ ਨਾਲ ਸੰਬੰਧਿਤ ਨਿਊਮੈਰੀਕਲ ਪ੍ਰੋਬਲਮਸ ਸੋਲਵ ਕਰਾਂਗੇ। ਆਸ ਹੈ ਕਿ ਤੁਹਾਨੂੰ ਯਾਦ ਹੋਵੇਗਾ ਕਿ ਅਲਫਾ ਪਾਰਟੀਕਲ ਦੇ ਹੈਡ ਔਨ ਕੋਲੀਜਨ ਲਈ ਅਪਰੋਚ ਦੇ ਦੌਰਾਨ ਨਿਊਕਲੀਅਸ ਅਤੇ ਅਲਫਾ ਪਾਰਟੀਕਲਸ ਵਿਚਕਾਰ smallest distance of closest approach ਕਹਾਉਂਦਾ ਹੈ। If the mass of an alpha particle is m and it approaches towards the nucleus of charge Ze with velocity v, then the distance of closest approach r0 is equal to 1 by 4 pi epsilon naught into 2Ze square upon half mv square। आओ इस उत्ते आधारित कुछ प्रॉब्लम्स देखते हैं। In a Geiger-Marsden experiment, what is the distance of closest approach to the nucleus of a 7.7 mega electron volt alpha particle before it comes momentarily to rest and reverses its direction? We know that throughout the scattering process, the total mechanical energy of the system consisting of an alpha particle and a gold nucleus is conserved. That is initial energy, which is the kinetic energy of the incoming alpha particle, is just equal to the final energy, which is the electric potential energy of the system. It is given that the maximum kinetic energy found in alpha particles is 7.7 mega electron volt or 1.2 into 10 to the power minus 12 joule. If r0 be the distance of closest approach, then using the relation r0 equal to 1 by 4 pi epsilon naught into 2Ze square upon half mv square, we get r0 equal to 9 into 10 to the power 9 into 2 into square of 1.6 into 10 to the power minus 19 into z upon 1.2 into 10 to the power minus 12, which is equal to 3.84 into 10 to the power minus 16 into z, where z is the atomic number of gold, that is 79. Hence, the value of r0 becomes 3.03 into 10 to the power minus 14 meter or 30.3 Fermi. The actual radius of gold nucleus is 6 Fermi. Since the distance of closest approach is considerably larger than the sum of the radii of the gold nucleus and the alpha particle, therefore, the alpha particle reverses its motion without ever actually touching the gold nucleus. My next problem is a 50 mega electron volt alpha particle approaching gold nucleus is deflected by 180 degree. How close does it approach the nucleus? Here, the energy of the alpha particle E is equal to 50 million electron volt, which is 8 into 10 to the power minus 12 joule, and Z is 79. Since the distance of closest approach r0 is equal to 1 by 4 pi epsilon naught into 2Ze square upon E, Therefore, R0 is equal to 9 into 10 to the power 9 into 2 into 79 into square of 1.6 into 10 to the power minus 19 upon 8 into 10 to the power minus 12. This is equal to 4.55 into 10 to the power minus 15 meter or 4.55 Fermi. चलो ਹੁਣ बोर्स मॉडल ऑफ हाइड्रोजन एटम ਦੇ मेन फीचर्स एक्सप्लोर करते हैं.
Electron in hydrogen atom moves in a circular orbit around the nucleus. ਇਹਨਾਂ orbits ਵਿੱਚ electrons ਦਾ angular momentum ਕੈਲਕੂਲੇਟ ਕਰਨ ਲਈ ਇੱਕ ਇੰਟੀਜਰ ਅਤੇ Planck's constant ਨੂੰ ਮਲਟੀਪਲਾਈ ਕਰਕੇ 2 ਪਾਈ ਨਾਲ ਡਿਵਾਈਡ ਕੀਤਾ ਜਾਂਦਾ ਹੈ, ਮੀਨਿੰਗ nth orbit ਦੇ ਇੱਕ ਇਲੈਕਟ੍ਰੋਨ ਦਾ angular momentum will be m(v(n) Rn, which is equal to nh upon 2 pi, where n is an integer. Electromagnetic radiation is given off or absorbed only when electron changes from one allowed orbit to another.
If the energy difference between the two orbits is delta E and nu is the frequency of the photon emitted or absorbed, then delta E is equal to h nu. If an electron of mass m, charge E, moving in nth orbit of radius Rn with speed Vn, then Vn is equal to n into h upon 2 pi m Rn and Rn is equal to n square into h square into epsilon naught divided by pi into m into e square. On substituting the values of Rn in the expression for velocity, we get Vn equal to 1 by 4 pi epsilon naught into 2 pi into e square upon n into h. To find the energy of an electron in an orbit, we simply calculate the total mechanical energy, which is the sum of kinetic and potential energies. The kinetic energy Ek of the electron in nth orbit is equal to half m Vn square. It is further equal to 1 by 8 pi epsilon naught into e square divided by Rn, whereas electrostatic potential energy Ep is equal to minus 1 by 4 pi epsilon naught into e square divided by Rn. Total energy En is equal to minus 1 by 8 pi epsilon naught into e square divided by Rn. On substituting the value for Rn, the equation for energy becomes En equal to minus m e to the power 4 upon 8 epsilon naught square n square h square. In general, we can write the value of total energy of nth orbit of hydrogen atom as minus 13.6 divided by n square electron volt. Let us now try some problems on Bohr's model. Experimentally, it is found that 13.6 electron volt energy is required to separate a hydrogen atom into a proton and an electron. Compute the orbital radius and the velocity of the electron in a hydrogen atom. Total energy of the electron in hydrogen atom is minus 13.6 electron volt. This is equal to minus 2.2 into 10 to the power minus 18 joule. Using the relation En equal to minus 1 by 8 pi epsilon naught into E square divided by Rn, we get minus 2.2 into 10 to the power minus 18 equal to minus 9 into 10 to the power 9 into square of 1.6 into 10 to the power minus 19 upon 2 Rn. This gives the orbital radius Rn equal to 5.24 into 10 to the power minus 11 meter. Therefore, the velocity of the revolving electron can be computed as 2.2 into 10 to the power minus 18 equal to half into 9.1 into 10 to the power minus 31 into Vn square, which gives Vn equal to 2.2 into 10 to the power 6 meter per second. The next problem is a 20 kg satellite circles Earth once every 6 hours in an orbit having a radius of 8,000 km. Assuming that Bohr's angular momentum postulate applies to satellites just as it does to an electron in the hydrogen atom, find the quantum number of the orbit of the satellite. We know that the angular momentum of a satellite in the nth orbit is mvn Rn equals to nh upon 2 pi. Here m is equal to 20 kg, Rn is equal to 8 into 10 raised to the power 6 meter, and orbital time period is 6 hours or 21,600 seconds. We also know that Vn is equal to 2 pi Rn upon T. This would give the quantum number of the orbit of satellite n equal to m into square of 2 pi Rn upon h into T. On substituting the values, we get n equal to 3.52 into 10 to the power 42. ਇੱਥੇ ਨੋਟਿਸ ਕਰੋ ਕਿ ਸੈਟੇਲਾਈਟ ਮੋਸ਼ਨ ਲਈ ਕੁਆਂਟਮ ਨੰਬਰ ਐਕਸਟ੍ਰੀਮਲੀ ਲਾਰਜ ਹੈ। ਹਾਂ, ਇੰਨੇ ਲਾਰਜ ਕੁਆਂਟਮ ਨੰਬਰਸ ਵਾਸਤੇ ਕੁਆਂਟਾਈਜ਼ੇਸ਼ਨ ਕੰਡੀਸ਼ਨਸ ਕਲਾਸੀਕਲ ਫਿਜ਼ਿਕਸ ਨਾਲ ਰਲਦੀਆਂ ਮਿਲਦੀਆਂ ਹਨ। The difference between the energies of any two orbits is therefore given by the equation delta E is equal to k times the difference of the square of the reciprocal of the orbit numbers, where k is proportionality constant for hydrogen atom whose value is 2.18 times 10 to the power minus 18 joule, and Ni is the number of initial orbit, whereas Nf is the number of final orbit. According to the Planck's equation, energy of a photon is equal to h nu or hc by lambda. When an electron falls or jumps from an orbit to another orbit, it emits or absorbs a radiation whose wave number is equal to the product of Rydberg's constant RH and the difference of the square of the reciprocal of the orbit numbers. Now, calculate the value of Rydberg's constant. Rydberg's constant is given as RH equal to me to the power 4 upon 8 epsilon naught square h cube c. On substituting corresponding values, we get RH equal to 1.097 into 10 to the power 7 per meter. Here is the next problem. The energy of hydrogen atom in its ground state is minus 13.6 electron volt. Determine the energies of those energy levels whose quantum numbers are 3 and 4. We know that the energy of hydrogen atom when the electron revolves in nth orbit is minus 13.6 upon n square in electron volt. In ground state, we take n equal to 1. Therefore, E1 is minus 13.6 upon 1 square, that is minus 13.6 electron volt. For n equal to 3, we get E3 equal to minus 13.6 upon 3 square, that is minus 1.51 electron volt. For n equal to 4, we get E4 equal to minus 13.6 upon 4 square, that is minus 0.85 electron volt. In our next problem, you have to tell me which level of the doubly ionized lithium has the same energy as the ground state energy of the hydrogen atom. Also, compare the orbital radii of the two levels. We know that the total energy of electron in nth orbit, En, is proportional to z square by n square. Therefore, the ratio of energies for lithium and hydrogen is the ratio of the squares of corresponding atomic numbers upon orbital number. For same energy levels corresponding to the ground state of hydrogen atom, orbital number of lithium must be 3. Furthermore, radius of nth orbit, Rn, is proportional to n square by z. Therefore, the ratio of the radius of the third orbit of lithium and the first orbit of hydrogen is 3:1. Let us try one more problem on Bohr's model. In this problem, you have to determine the speed of electron in fourth orbit of helium plus. Is the non-relativistic approximation valid? We know that the speed of electron in nth orbit is Vn equal to 1 by 4 pi epsilon naught into 2 pi Ze square upon Nh. For helium, Z is 2 and N is given as 4. Therefore, on substituting the corresponding values, we get V4 equal to 1.096 into 10 to the power 6 meter per second. Whereas, the ratio of V4 and the speed of light is 0.0365, which is much less than 1. Hence, non-relativistic approximation is true. Bohr's model ਨਾਲ related ਸਾਡਾ ਅੱਜ ਦਾ ਅਗਲਾ important concept ਹੈ ਹਾਈਡਰੋਜਨ ਐਟਮ ਦੀ spectral series. ਹਾਈਡਰੋਜਨ ਐਟਮ ਦੇ ਹੀ spectrum ਨੂੰ spectral series of hydrogen atom ਕਿਹਾ ਜਾਂਦਾ ਹੈ. ਆਓ ਇਸ series ਨੂੰ ਇੱਕ ਕਰਕੇ discuss ਕਰੀਏ.
Shortest wavelength ਦੀ series ਨੂੰ Lyman series ਕਿਹਾ ਜਾਂਦਾ ਹੈ. ਇਸ series ਦਾ ਫਾਰਮੂਲਾ ਹੈ wave number equal to Rydberg's constant into 1 upon 1 square minus 1 upon n square, where n is equal to 2, 3, 4 and so on. Lyman series ਨਾਲੋਂ ਵੱਧ wavelengths ਵਾਲੀ series ਨੂੰ Balmer series ਕਿਹਾ ਜਾਂਦਾ ਹੈ. ਇਸ series ਦਾ ਫਾਰਮੂਲਾ ਹੈ wave number equal to Rydberg's constant into 1 upon 2 square minus 1 upon n square, where n is equal to 3, 4, 5 and so on. Balmer series ਨਾਲੋਂ ਜ਼ਰਾ ਵੱਧ ਵੇਵਲਿੰਗਸ ਵਾਲੀ ਸੀਰੀਜ਼ ਨੂੰ ਪਾਸਚਨ ਸੀਰੀਜ਼ ਕਿਹਾ ਜਾਂਦਾ ਹੈ। ਇਸ ਸੀਰੀਜ਼ ਦਾ ਫਾਰਮੂਲਾ ਇੰਜ ਲਿਖਿਆ ਜਾਵੇਗਾ: wave number equal to Rydberg's constant into 1 upon 3 square minus 1 upon n square, where n is equal to 4, 5, 6 and so on. Paschen series ਤੋਂ ਅਗਲੀ ਯਾਨੀ ਇਸ ਤੋਂ ਜ਼ਿਆਦਾ wavelength ਵਾਲੀ series bracket series ਕਹਾਉਂਦੀ ਹੈ। Bracket series ਦਾ ਫਾਰਮੂਲਾ ਹੈ wave number equal to Rydberg's constant into 1 upon 4 square minus 1 upon n square, where n is equal to 5, 6 and so on. ਸਾਰਿਆਂ ਦੇ ਅਖੀਰ ਵਿੱਚ ਬ੍ਰੈਕਟ ਸੀਰੀਜ਼ ਤੋਂ ਵੀ ਵੱਧ ਵੇਵਲੈਂਥਸ ਵਾਲੀ ਸੀਰੀਜ਼ ਨੂੰ ਫੁੰਡ ਸੀਰੀਜ਼ ਦਾ ਨਾਂ ਦਿੱਤਾ ਗਿਆ ਹੈ। ਇਸ ਸੀਰੀਜ਼ ਦਾ ਫਾਰਮੂਲਾ ਹੈ wave number equal to Rydberg's constant into 1 upon 5 square minus 1 upon n square, where n is equal to 6, 7 and so on.
Our next problem is calculate the shortest and longest wavelength in the Paschen series of hydrogen atom. We know that the formula for different spectral lines in Paschen series is 1 by lambda equal to RH into 1 upon 3 square minus 1 upon n square, where n is equal to 4, 5, 6 and so on. And the value of RH is equal to 1.097 into 10 to the power 7 per meter. For shortest wavelength, n is infinity and 1 by lambda becomes equal to 1.097 into 10 to the power 7 into 1 by 3 square minus 1 by infinity square. That is 0.12189 into 10 to the power 7 per meter, or lambda is 8.2042 into 10 to the power minus 7 meter, or 8204.2 angstrom. For longest wavelength, n is 4 and 1 by lambda becomes equal to 1.097 into 10 to the power 7 into 1 by 3 square minus 1 by 4 square. That is 0.5333 into 10 to the power 7 per meter, or lambda is 18.7524 into 10 to the power minus 7 meter, or 18,752.4 angstrom. Let's try one more problem. Using Bohr's formula for energy quantization, determine first the longest wavelength in Lyman series of hydrogen atom spectrum, and second the excitation energy of the n equal to 3 level of helium atom. Third, the ionization potential of the ground state of lithium atom. According to Bohr, the wavelength of the emitted radiation for Lyman series is 1 by lambda equal to RH into 1 upon 1 square minus 1 upon n square, where n is equal to 2, 3, 4 and so on. And value of RH is equal to 1.097 into 10 to the power 7 per meter. for longest wavelength. N is 2 and 1 by lambda becomes equal to 1.097 into 10 to the power 7 into 1 by 1 square minus 1 by 2 square, that is 0.8228 into 10 to the power 7 per meter, or lambda is 1.2154 into 10 to the power minus 7 meter, or 1215.4 angstrom. Excitation energy, that is the energy required to jump the electron from ground state to the third level of helium atom, is delta E equal to 2.18 into 10 to the power minus 18 into Z square into 1 by Ni square minus 1 by Nf square joule. Here Ni is 1, Nf is 3 and Z is 2. Therefore, excitation energy of helium atom is delta E equal to 2.18 into 10 to the power minus 18 into 4 into 1 by 1 square minus 1 by 3 square joule. This is 7.751 into 10 to the power minus 18 joule, or 48.44 electron volts. Let us now calculate the ionization energy of ground state of lithium atom. Here lithium atom has 3 electrons, out of which 2 are in first orbit and 1 is in second orbit. It means lithium atom is doubly ionized, as 2 electrons are already removed. The third electron has to be removed from ground state to infinity. Therefore, ionization energy for lithium is delta E equal to 2.18 into 10 to the power minus 18 into Z square into 1 by 1 square minus 1 by infinity square joule. Here Z is 3. Hence, delta E is equal to 2.18 into 10 to the power minus 18 into 9, which is 19.62 into 10 to the power minus 18 joule, or 122.625 electron volt. Let us now have a look on one more problem on this. In a neon atom, the energies of the 3s and 3p states are 16.80 electron volt and 19.20 electron volt respectively. What is the wavelength corresponding to 3p-3s transition in the neon atom? Since the emitted energy is the difference of energies of two states, therefore, the emitted energy delta E is equal to 19.20 minus 16.80, that is 2.40 electron volt, or 2.4 into 1.6 into 10 to the power minus 19 joule, which is 3.84 into 10 to the power minus 19 joule. According to Planck's equation, wavelength lambda is equal to hc upon energy of the photon. Therefore, lambda is equal to 6.6 into 10 to the power minus 34 into 3 into 10 to the power 8 upon 3.84 into 10 to the power minus 19 meter. This is equal to 5.1563 into 10 to the power minus 7 meter, or 5156.3 angstrom. Let's calculate the energy of a single photon of red light with a wavelength of 700.0 nanometer and the energy of a mole of these photons. Here, wavelength of red light is 700.0 nanometer. Substituting this value into the Planck-Einstein equation gives the value of energy as equal to 2.829 into 10 to the power minus 19 joule. A single photon of red light carries an insignificant amount of energy, but a mole of these photons carries about 1,70,336.6 joules of energy, or 170.34 kilojoule per mole. आस है कि ਹੁਣ ਤੁਹਾਨੂੰ ਐਟਮਸ ਨਾਲ ਰਿਲੇਟਡ numerical problems solve ਕਰਨ ਵਿੱਚ ਮੁਸ਼ਕਿਲ ਨਹੀਂ ਆਏਗੀ. See you in the next class. Goodbye.